Hello and welcome everyone. Thank you for taking the time to listen to this talk on my work for the AAAI conference titled Every Component Counts, Rethinking the Measure of Success for Medical Semantic Segmentation in Multi-Instance Segmentation Tasks. My name is Alexander Jaus and I will guide you through this presentation. The scenario that we will look at in this work is the segmentation of tumors, or also called lesions, in volumetric image analysis. Volumetric images are something like the CT or the MRI. And training semantic segmentation model has become the standard to analyze these type of images. And the analysis of tumor volume or lesions is no exception. This, however, poses difficulties on how we actually should evaluate these semantic segmentation models, because for semantic segmentation, we aim to optimize the overlap. However, the overlap may not be a very suitable criteria for determining the importance of individual lesions, as even small lesions can have significant effects on the life of the patient and the treatment that the patient is currently undergoing. Here again, we can see that when we only have a single tumor and we want to segment it within a very restrictive type of scenario, for example, during a challenge, where we know we have the kidney and within the kidney there is one tumor, then it is perfectly fine to use semantic segmentation evaluation metrics, as the overlap here would also reflect in some form the detection performance of the model. However, when we look in the clinic or when we look in the scenario where we have like whole body scan and our goal is really to identify all the regions, we are rather in the task that you could call detection via segmentation. And there we're also interested in finding all these small lesions that may not be of very high importance for the DICE score or any semantic segmentation score. However, for the patient's life and the treatment plan, they can be detrimental. Let's first of all look at which type of metrics are there for semantic segmentation, and in the following we will look at their problems. So commonly are overlap-based metrics like the DICE or the IOU, and it's easily imaginable that they are biased towards large metastasis as they aim to measure how well the global overlap is. Second type of metric are distance-based metrics such as Hausdorff distance, and the Hausdorff distance is oriented towards the extreme points as it measures how well the largest distance between two set of points is. And they're rather suitable to compare one connected ground truth component to one predicted component, which again is not really the case in the scenario where we have many metastases and many predicted components. And you may say, okay, what about something like the Hausdorff 95 distance or the normalized surface distance? And also these type of metrics are influenced by the size of the objects, as they would typically measure the difference between the surface points, and large components have more surface points and therefore have a larger effect on the distribution of the surface distances. Another type of metric are unified metrics, which aim to unify detection and segmentation. Examples here are the panoptic quality or the Brett's lesion dice. And these aim to connect detection plus segmentation metrics. And what is required for them is that they assign predictions to ground truth components. And they typically do that by overlap. So for example, the panoptic quality matching criteria aims to or requires a segment to have at least 0.5 IOU overlap to be counted as a true positive. And in this scenario here, for example, this upper prediction would be counted as a false positive as it falls below this threshold. This 0.5 IOU threshold is important to guarantee a unique matching between the true positive, between the predictions and the ground truths. Lesion dice, on the other hand, which is a recently introduced metric, alleviates this threshold of 0.5 and allows the matching of multiple true positives, which has advantages, but again also disadvantages. And the inspiration and the idea that we have for the CC metrics approach is that in volumetric images, the distance between two voxels in the image space is always in constant relation to the distance of the real-world coordinates of these two pixels or these two voxels. Because, as you can also see in the video here, two of the voxels will always correspond to the same distance in the real world. Because this is the way the image was captured. And for example, in perspective 2D images, this is not really the case. For example, in the foreground, two voxels may only represent objects that are 1 centimeter apart in the real world, whereas in the background of the image, they may be like a kilometer apart from each other. And this property can be exploited, and this is also what we do in CC metrics. This observation is also the cornerstone on which we build the CC metrics evaluation protocol. For CC metrics, we partition the image into distinct regions based on the ground truth connected components. For example, here we have 3 connected components, which means that we will partition the image into 3 distinct spaces and map each point in space to its closest ground truth component. To evaluate the models then using the CC evaluation protocol, we will only consider the prediction that fall within each region and map them to the ground truth component. So this limits the prediction of the models to their closest ground truth components, thereby also guaranteeing a unique matching. Here's an example on how this Voronoi-based evaluation regions may look for a patient with a couple of metastases. The Voronoi regions can be computed efficiently using a Euclidean distance transform. Now let's look at the comparison between some standard metrics and their CC counterpart. Initially, we assume that we have a ground truth and a perfect prediction, which we will then iteratively degrade and making it worse by applying erosion. Now let's look at the graph. Initially, we can see that all the metrics start with a perfect initial score and then they get worse. However, when we look at the standardized, we see that the standardized score is largely dominated by the largest component. The largest component is shown in this upper dashed line. CC dice drops quicker and somewhat reflects the average of these 3 dashed lines, which represent the individual dice for the 3 connected components. And we also have a look at panoptic quality, which also decreases at first quickly, which is a nice property. However, then we also see these discontinuities here, and we will have a look at what they are, why they're like this, and what causes them in the following slide. And in order to understand better what is happening with the panoptic quality measure, we will only now perform erosion on the smallest component. Again, we can see that the standard dice is not affected at all, basically. CC dice quickly drops to a score of 2/3, which is exactly what we want. And the panoptic quality also initially drops quick, which is nice, but then it also has these large drops at some point, and it also has this increase. So to understand what's happening here, we will look at the formula, and we can see that at some point, the true positive component will turn into a false positive component as soon as it falls below the 0.5 IOU threshold. Then suddenly it is no longer considered for the IOU, and it suddenly increases this denominator part here, and therefore we have a sharp decrease, which we find unpleasurable, as the difference here is only a couple of pixels. And then also it stays uninformative the whole time here while it is a false positive, and then increases again as soon as the component is completely eradicated, because now it is no longer a false positive. And this is also an undesirable property, as this metric would then favor not predicting anything at all, than having a prediction that is below a certain threshold. When we compare Hausdorff distance, we see a similar image. Again, we apply erosion to the smallest and the largest component. So when we erode the largest, we can see that this drives the score mainly. However, if we erode the smallest component, the standard HD95 is not affected at all. And again, using the CC metrics evaluation protocol, we can see now that it does not matter if we erode the largest or the smallest component. Both scores now would behave almost the same, which is exactly what we want. Now, what happens when we evaluate networks using the CC metrics evaluation protocol? For example, when we evaluate on AutoPAD, which is a high metastasis count dataset, we can see that there sometimes are large difference between dice and CC dice, and also large difference between the other scores. For example, NNUNet performs about 20% worse using CC dice, which then indicates that it is largely biased towards large metastasis. However, what is also interesting is that, for example, other networks, when we would select them based on dice, we would get a different order than if we select them by CC dice, which also indicates that CC dice does bring a lot of additional value to the table. This is also true for the other metrics under the CC evaluation protocol. When we look at the low metastasis count data set, like Hector, which only has 1 or 2 lesions, we can see that the metrics are mostly well aligned. Here's also an example of a case where the dice is lower than CC dice. And for example, we can see that there's a larger component predicted here. However, which is a false positive. However, the 3 small ones are aligned quite well. And so CC dice does not punish this that severely, as overall the 3 components are well addressed. However, the standard dice somehow is drawn down a lot by this prediction here. On the other hand, we very often also have the case when dice is a lot larger than CC dice, and this is typically the case when we have a large tumor mass that is predicted okay-ish, but some of the small components and some of the small metastases are missed by the network. The take-home message for this presentation should be that CC metrics is a useful protocol to report alongside with the standard metrics, as it offers a glimpse in how the network performs if each metastasis was equally important. And we hope that this will allow you to make better and more informed decisions on which network to choose and to get a glimpse into how the real clinical performance of a network could be. Also, CC dice, for example, and also the other CC metrics do provide additional information to dice, so they're not perfectly correlated or anything, and the correlation, of course, decreases with the number of the metastases. These are the references that I used, and thank you for your attention. Let's connect. If you have remaining questions, I'm always happy to receive your mail, or you will also find me at my poster. Thank you.